Why do systems designed for peak performance so often end in catastrophic failure? The answer lies in a hidden fragility, a weakness that's built directly into the process of optimization itself. It's a common expectation. A system performing at its best should be inherently strong. We see efficiency, productivity, and stability as clear signs of robustness. But the reality is more complex. Every gain in performance actually creates a trade-off. Pushing a system to excel in one area can, and often does, weaken it in another, creating vulnerabilities that are rarely obvious at first. So, to understand this trade-off, we first need to look at the universal pressures that shape any complex system. You see, every system operates under constraints. Think of limited resources, competitive environments, or even just the basic laws of physics. These external forces are always there, constantly pushing on the system, forcing it to do more with less. And in order to function effectively within those constraints, a system has to adapt. It has to optimize. This means finding the most efficient pathways and eliminating anything that looks like waste or redundancy. Through this process of optimization, the system becomes more and more specialized, really honing its ability to do one specific thing under very specific conditions. But this process of optimization isn't random. It's guided. And to guide it, you first have to define what performance even means. This requires establishing metrics, clear, quantifiable measures of success, like output, speed, or cost. And right here, we find the critical first step toward fragility, because you see, no metric can ever capture the full complexity of reality. Measurement always creates a simplified model, a proxy for the real world. We end up measuring what's easy to quantify, which naturally focuses attention on the most common, predictable, and, well, average cases. The irregular, unpredictable extremes, they're simply left out of the model. Now, this intense focus on simplified metrics creates a really powerful feedback loop, one that pushes the system relentlessly towards specialization. This dynamic has a name, the performance paradox. It's a simple but powerful idea. As soon as a measure becomes a target, it ceases to be a good measure. Why? Because the system learns to game that specific metric, often at the expense of the actual, broader performance it was meant to represent. This unfolds through a four-step process. First, a metric is established. Then, the system adapts to maximize its score on that metric. As it gets better, the performance variability across the system starts to shrink. Everyone starts doing well on that one dimension. And finally, because there's so little variation left, the metric itself becomes less informative. It can no longer tell you the difference between good and bad performance. The end result of this cycle is a system that becomes exquisitely adapted to a very narrow band of predictable, average conditions. It becomes a specialist, perfectly tuned to operate in the world as it's described by its own simplified measurements, and not necessarily the world as it actually is. But this high degree of specialization always comes at a cost. It creates a fundamental trade-off, a trade-off between performance in expected conditions and the ability to survive the unexpected. To really get this, we need to clearly distinguish between three related but very distinct qualities of a system. First, there's reliability. This is simply the ability of a system to work as designed, but only under specified conditions. It's about performing correctly when everything is normal, and this is the main target of most optimization efforts. Next, we have robustness. This is a bit broader. It's the ability to work under anticipated variations. It handles the known problems, the things you expect might go wrong, and have a plan for. And finally, there's resilience. This is something else entirely. It's the capacity to survive unanticipated events, shocks that completely violate the system's core assumptions about how the world is supposed to work. So, when a system optimizes based on metrics, it naturally prioritizes reliability and robustness. And the reason is simple. You can measure them. Both can be defined, specified, and tested for. You can create a requirement for them and then verify that the system meets it. But resilience, that's much harder. By its very definition, you can't specify a plan for the unknown. And so, in the relentless drive for efficiency, the very things that create resilience, things like redundancy, slack, or diversity, start to look like waste. And what do you do with waste? You optimize it away. The system makes a trade. It sacrifices its ability to handle the unknown for better performance in the known. And this trade-off isn't just a theoretical idea. It physically manifests as a structural change within the system, creating that hidden fragility we talked about earlier. Network theory gives us a really clear way to visualize this. Imagine a random network where all the connections are spread out pretty evenly. This kind of network is actually quite resilient. You can remove nodes, even a few important ones, and it doesn't just fall apart. But an optimized network often evolves into something different, a scale-free or hub-and-spoke structure. Now, this is incredibly efficient and robust against random failures, but its total reliance on a few critical hubs creates a profound, single-point vulnerability. That targeted attack on a central hub, well, that's the network's version of an extreme, unanticipated event. It's exactly the kind of shock the system was never designed, measured, or optimized to handle. In fact, its very strength in dealing with average, random disruptions becomes the source of its critical weakness to one single, well-placed blow. This type of collapse was famously termed a normal accident by the sociologist Charles Perrow. His argument was that in very complex and tightly coupled systems, a massive failure isn't some rare anomaly caused by a mistake. No, it's an inevitable, emergent property of the system's structure itself. The same efficiency that links everything together so tightly also creates the perfect pathways for a tiny local failure to cascade catastrophically through the entire system. And we can see this concept demonstrated directly. In the random network, losing one node is just a local problem. The network stays connected. But in the optimized network, losing that central hub is a systemic catastrophe. The entire structure, designed for peak efficiency, simply fragments and collapses. This is the very nature of emergent fragility. All of this leads us to a final and somewhat paradoxical principle about the nature of these systems and the hidden consequences of what looks like successful design. The core dynamic really boils down to this. An optimized system achieves incredibly high efficiency when it's dealing with the average events it was built for, but in doing so, it develops a high degree of fragility when faced with extreme events it never anticipated. It's the fundamental trade-off. You can design for performance, which sacrifices resilience, or you can design for resilience, which sacrifices performance. You can't maximize both. So, in the end, we shouldn't view large-scale systemic failure as just a correctable flaw or the result of some isolated mistake. It's something more fundamental. It is a natural, emergent consequence of the system's own success. Success, that is, at optimizing for a predictable world that was defined by simplified measurements. The very process that makes a system strong, efficient, and reliable for the average is precisely what makes it fragile at the extremes.